Hello, I am Rahul Baghel, Assistant Professor, Chhattisgarh Swami Vivekanand Technical University, Bhilai. Welcome you all to the course on Industrial Automation and Drive. Today, we begin with our 20th lecture on Star Delta Starter and their PLC programming. In the previous lectures, Dr. Simpir Allahan ma'am has already covered the basic principles of electrical machines and provided detailed insights into AC and DC machines. As we all know, induction motors are widely used in industries compared to the other types of motors. The reason for these are robust and durability. Under this, the simple construction and the low maintenance are come. Induction motors have a simple design with fewer moving parts compared to the other types of motors. This makes them less prone to mechanical failures and wears, resulting in longer lifespan. Less maintenance. They don't have brushes or commutators, which are components that wear out time in the other types of motors like DC motors. Next is high efficiency. Under this, energy efficiency and the better power factor will come. Induction motors are highly efficient, especially when operating at or near full load. Their efficiency is typically above 90%, which is important for industries where motor run for long hours and energy costs are significant. Induction motor generally have a good power factor, which is crucial in industrial application to minimize energy losses and improve the efficiency of power uses. Next is cost effective, lower initial cost. Induction motors are less expensive to manufacture than the other types of motors such as synchronous or DC motors. This makes them a cost effective option for many industrial applications. Next is operating cost. Their high efficiency and low maintenance requirements also translate into lower operating cost over time. Next reason is wide availability and standardization. Standardized design. Induction motors are widely available in standard size and rating, making it easily for industries to replace or upgrade motors without the need of custom designs. Next is global acceptance. They are universally accepted and used, meaning spare parts and technical supports are readily available worldwide. Next is versatility, wide range of applications. Under this, induction motors can be used in variety of industrial applications from driving pumps, fans and compressors to powering conveyor belts, cranes and mixers. They are suitable for both constant speed and variable speed applications. Adaptability to harsh environment. Induction motors are capable of operating in tough environment, including areas with dust, moisture and high temperatures, making them suitable for industries like mining, manufacturing and chemical processing. Next is safety. Unlike the brushed motor, induction motors do not produce a spark during operation, making them safer to use in environment where the flammable materials or gases are present. Overload tolerance. Induction motors can tolerate short-term overloads better than many other types of motor, which is important in industrial setting where load condition can varies. Next is a self-starting. Induction motors are inherently self-starting, meaning they don't require additional components like brushes or permanent magnets to initiate rotations. This simplifies their use in industrial applications. We prefer star delta starters for starting induction motors. These starters are essential due to the following factors. First one is high starting current. When a large motor is started directly, it can draw a starting current that is 6 to 10 times higher than its normal running current. This high inrush current can cause significant voltage drop in power supply systems, potentially affecting other equipments connected to the same supply. Under this, next one is electrical stress. The high current can put stress on electrical components like circuit breaker, fuses, and transformers, which may lead to overheating or even failure. Second one is mechanical stress. Under this, first one is torque impact. Along with high current, direct starting also generate a high starting torque, which can cause mechanical stress on the motor and the driven equipment. This can lead to excessive wear and tear, reducing the lifespan of machinery. Next is shock load. The sudden application of full torque can result in a shock load to mechanical parts like gear, belts, and coupling. Next reason is energy efficiency. By using a star delta starter, the motor initially runs at reduced voltage, which means lower current and torque. This controlled start reduce energy wastage and can be more efficient in certain applications. Next reason is system stability. Under this, voltage stability is first. In industrial setup, multiple motors may be connected to the same power system. If all these motors start simultaneously with full voltage and combined inrush current can cause significant fluctuation in the power supply, affecting the stability of entire electrical system. Next one is preventing voltage sag. The star delta starter helps in minimizing this voltage sag, ensuring a more suitable and reliable power supply. Next reason is compliance with regulations. In many regions, electrical codes and standards requires the use of starting methods that limit inrush current to protect both the electrical infrastructure and connected devices. The star delta starter is common and compliant method to meet these requirements. As you can see in the diagram, the star delta starter is shown. This is the actual diagram of a star delta starter, right? Now let's the operation of a star delta starter. This starter work by initially connecting the motor winding in a star configuration, which reduces the voltage across each winding to 1 by root 3, that is approximately 58% of the full line voltage. This reduction in voltage leads to a significant decrease in the starting current, typically to above 1/3 of what it would be if the motor were started directly in the delta configurations. This lower current reduces the electrical stress on the power supply system, preventing issues such as voltage drip, which could affect other equipments connected to the same power network. When the motor is first energized, it operates in the star configuration. During this phase, not only in the starting current reduced, but the torque produced by the motor is also lower. This is beneficial because it reduces the mechanical stress on both the motors and the machinery it drives, leading to a smoother and less stressful starts. The star connection allows the motor to gradually accelerate without the high initial torque that could potentially damage the mechanical components. Once the motor reaches approximately 80% of its full load speed or full speed, a timer or other control mechanism triggered the transition from the star configuration to the delta configuration. At this point, the motor winding are reconnected in a delta configuration, which allows each winding to receive the full line voltage. This change enables the motor to produce its full rated torque and run at its full speed. The transition from star to delta is usually seamless, although there is often a brief moment of reduced torque during the switch, which is most application is not problematic. The star delta starter system typically consists of three main contactors, as you can see in the diagram also. One for the star connection, one for the delta connection, and one for the main power supply. A timer is used to control the duration of the star phase before switching to delta. Additionally, an overload relay is incorporated to protect the motor from overcurrent situation by disconnecting the power if the current exceeds a safer limit. Now, let's see the PLC program or ladder logic for the star delta starters. As you can see in the diagram, in the first rung, the start switch is represented by I colon 0/0 and the stop switch is represented by I colon 0/1, and beside them the OLR means overload relay is represented by I colon 0/2. In the first rung, you can see the latching is also provided to the start switch with the main contactor, and in the second rung you can see the main contactor is connected to the T-on timer. The address of the timer is represented by T4 colon 0. Time base is 1 second and we are using the preset value of 10 second. In the third rung, you can see the main contactor is connected to the star connection, and in this rung you can see the two NC switch means two interconnections are provided. One is for the timer done bit, that is T4 colon 0/done bit, and one for the delta connection in form of NC switch, normally closed switch, right? And you can see in the last rung the done bit of timer is connected with the delta connection, and in this rung also one interconnection of star connection is also provided. As you can see in the diagram, the NC switch of a star connection is also connected in the fourth rung, right? So let's take the first case. When the start is 0, means we are not changing the state of start switch, it remains in the normally open condition. That's why the main contactors doesn't get any supply. That's why my timer is also doesn't get any supply, and if the timer doesn't get any supply, it doesn't start counting. That's why accumulator is equals to 0, and you can see the star connection which is connected to the done bit of timer is also doesn't get any supply. That's why it also represented by the 0, right? Let's take the next case. When I press the start button or when I change the state of a start switch from normally open to normally close, you can see my main contactor gets the supply. That's why my timer also getting the supply and it start counting for 10 seconds. So you can see the accumulator value is changing from 0 to 10, right? At the same time, you can see my star connection is getting supply. That's why my the start connection is getting supply. That's why you can see in the third rung the output is represented by 1, right? And you can see in the fourth rung when a star connection is high, in the fourth rung it represented by the normally close. That's why it creates the fourth rung is open. That's why my delta connection doesn't get any supply because of the interconnection, right? So in this case, when I press the start switch, my main contactor gets the supply and my timer start counting for the 10 second. For the 10 second, my motor is connected in the star connection, right? After 10 second, you can see when the timer provides the done bit, you can see the fourth rung is getting supply and the third rung is just doesn't get any supply because of the done bit is connected in the NC switch, right? So in the fourth rung you can see when the done bit is high after 10 second, my delta connection is on, and because of the interconnection the third rung goes 0 and the star connection goes 0, right? Let's take the fourth case. Suppose the OLR is 1 in the running condition, means overload condition happens in the running condition. You can see here when OLR is 1, the main contactor is 0 because OLR is connected to the main contactors. When the OLR is 0, main contactor also becomes 0, and when the main contactor becomes 0, my T-on timer goes 0, and because of the T-on timer goes 0, my star connection goes 0, right, and the motor will stop, right, as per the operation of the motors. Next case, suppose when I press the stop switch, is also similar because a stop switch and OLR switch is connected in series. So when I press the stop button, my main contactor also doesn't get any supply, and because of that my motor will stop, right? So this is the operation of my star delta starter in PLC programming, right? And next we will see the move and the logical instructions. Under this, the first instruction is MOV instructions. As you can see in the diagram also, the MOV instruction is connected in the first rung in the output side. So MOV is the output instruction, and you can see in the diagram the MOV instruction takes one input and provides one output, one input in a form of source and one output in a form of destination. The source address is represented by N7:0 and the destination address is represented by N7:1. In the same, you can see in the diagram also, the data file is also represented, right? And you can see the value of the N7:0 is 5, right? So means when I provide the supply to the move instruction, my move instruction changes the source value to the destination value. Initially the destination value is 0. So when I provide the supply to the move instruction by the switch, which is denoted by I:0/0, right? So when I press the switch, my destination address changes, my value of the destination address changes by 5. As you can see in the diagram, initially the value of the destination address is 0, and after when I press the switch 1, you can see the value of the destination address is changed by 5, right? Next instruction is A and D instruction, and it represented the bitwise AND instructions. You can see in the diagram, in the first rung, you can see the AND instruction is connected with the switch I:0/0, and you can see the diagram also. The AND instruction takes two inputs in the form of source A and the source B. The first address of input is represented by N7:0 and the second input is represented by N7:1. and the one output is represented, the destination is represented by N7 colon 2. Initially, I set the value of first input is 6 and the value of second input is 2, and you can see the data files in the binary form. You can see the 6 is represented by, in a 4-bit binary, it is represented by 0110, right? And the 2 is represented by 0010. So what happened here, when I press the switch, it provides the bitwise AND operations. It starts the bitwise AND operation and provides in the destination address the AND operation, bitwise AND operations. You can see in the diagram, when I press the switch I colon 0/0, you can see the data files is changes by the bitwise AND operations, right? The bitwise AND operation means you can see the first bit is 0 and 0, N7 colon 0 and N7 colon 1. You can see the both address first bit is 0. That's why when AND gets the 0 input, the outputs of AND gate is 0, right? So similarly, you can see the second bit is 1. So the AND operation is 1 and 1 when we provide 1 and 1 as an input. So we are getting the output is also 1. That's why the output is also 1, represented by 1, right? In the address of N7 colon 2. And similarly, you can see the third bit is 1 and 0. So the AND operation of 1 and 0 provides the output is 0. That's why you can see in the diagram the output is 0. And the fourth bit is also 0. That's why the AND operation of 0 input is also 0. That's why output is 0. So you can see here, when we will give the 6 and 2 as an input to the source A and source B, we are getting the output in form of binary, that is 2, that is 0010. You can see in the binary form of output as in address N7 colon 2, right? Next instruction is OR instructions. It also provides the bitwise OR instruction or operations. So in these case also, we took two address for the input, that is N7 colon 0 and N7 colon 1, and one address for the output, that is N7 colon 2, represent the output address. The value of the two input is represented by 6 and 2 in the binary form. 6 is represented by, as same I'll explain, the 0110, and 2 is represented 0010, right? So initially, when if OR instruction doesn't get any supply, its output is 0, as you can see in the diagram. And when we press the input switch, that is I colon 0/0, it changes the bitwise, or it operates the bitwise OR operations. And you can see in the diagram, the first bit is 00. So the OR operation of 00 provides the 0 as an output. And the next bit is, you can see the 11. The OR operation of 11 provides the 1 as the output. So you can see the output is represented by 1, and the third bit is represented by 10. So the OR operation of 10 represent the output by 1, right? And similarly the fourth bit is represented by 00. So the output of OR gate or OR operation of 00 input is 0. That's why we are getting the final output is 0110, right? So final output is 0110, that is 6. You can see in the diagram, right? So the output is 6 when we provide the input 6 and 2. Next, take the another instruction, that is XOR instruction. It also provides the bitwise XOR for the two inputs, as you can see in the diagram also. Here also the two inputs, the source A and source B, and the one output in the form of destination. In this case also we are using the two inputs are 6 and 2, and the address is also same, N7:0 and N7:1, right? The destination address is also represented by N7:2 as the previous instruction we are using. So in this case also the value of source A is 6 and the value of source B is 2, and you can see in the diagram the data file is also represented in the binary form, right? So initially when the XOR doesn't get any supply, the output is 0. You can see in the diagram in the next case, when I provide the input to the XOR gate or XOR instruction, you can see the first bit is 0 0, that's why output is 0, and the second bit is 1 1, that's why again the output is 1, because in the XOR gate we are getting outputs when the both inputs are different. And you can see in the third bit, one bit is 1 and another bit is 0, so the output is 1. And similarly the fourth bit, you can see fourth bit is 0 0, that's why output is 0, right? So it provides the bitwise XOR operation and provides the final output. So we are getting output, as you can see in the data files, 1 0 0, right? Next instruction is NOT instruction. It also provides the bitwise NOT. So in this case you can see it takes one input and provides one output. Address of one input is represented by N7:0 and the output address is represented by N7:1. Initially we provide 12 as an input, and you can see in the data files in the binary form of 12 is represented 1100, right? So initially when my NOT gate doesn't get supply, you can see the output is 0, and in the next case when I provide the input, you can see the I:0/0 is 1, my output is changes. The bitwise NOT operation means 0 is converted to the 1 and 1 is converted to the 0. So you can see my output is represented by 0 0 and 1 1, or in form of decimal you can say it changes by -13. You can see the move and logical instructions. In these case, in these instructions we see MOV instructions, AND instructions, OR instructions, XOR instruction and NOT instructions. Move instructions provide means changes the destination address by the source address, and in the AND, OR and XOR instructions provides the bitwise AND operation, OR operation, XOR operation and XNOR operations, right? So that's all for the today's lectures. In this lecture we covered the star delta starters and their importance and their PLC programming, and the move and logical instructions. In the next session we will explore more on the mathematical instruction in PLC programming and their applications. Thank you and happy learning.